Hi there. In this video we'll have a look at the exam of optimization methods of June 2023. As usual, we'll only look at the exercises, so for the theory you should refer to the theoretical course. Without further ado, we'll start with questions 1 and 4. For question 1, you have to find the local extrema and saddle points of the function that is shown on the screen. Question 4 is about numerical optimization. You have to apply the Newton descent method for this same function with c fixed to 2, and you have to perform the first iteration with a step size equal to 1 starting from the initial point that is given on the screen. As usual, if you're preparing your exam, you should try to do this by yourself and push the pause button. Well, let us have a look at the solution first of the first question over here. Of course, we have to compute the gradient, which is the first derivative. We have to take the partial derivatives with respect to x, this is this one, and with respect to y, and this is this one. And then we have to take second derivatives, right? And this leads to the Hessian, which is a 2 by 2 matrix. So let us have a look at the critical points, right? And the critical points are the values of x and y that make the gradient 0. And you can kind of easily see that, well, x and y both 0 will give a 0 gradient. But this is also the case if you plug in x is equal to c and y is equal to c. So we have our two candidates, right? And now we have to plug these values in the Hessian and decide whether we have a saddle point, a minimum, or a maximum. So let us start with the first point over here, which is the origin. If we plug this in the Hessian, this is what we obtain. And as usual, if you work with 2 by 2 matrices, the easiest thing to do is to look at the determinant, because this is the product of the eigenvalues, and the trace, because this is the sum of the eigenvalues. So we see here that we have a product that is negative, c square is positive, and we have a minus sign in the determinant. So the product is negative, and the trace is 0, the sum is 0. So we have two eigenvalues with opposite sign, right? So this means that the Hessian in P1 is non-definite, so we have here a saddle point. We can do something similar for the second solution, the second critical point, P2 over here. If we plug in the values, this is the value of the Hessian. Same exercise, we compute the determinant, the trace, and now we see that we have a positive product, and we have a sum of the eigenvalues that is 12c. So depending on the sign of c, we'll have either, if c is positive, two positive eigenvalues, right? Then this means that the Hessian is positive definite, and P2 is then a minimum. But if c is negative, right, we'll have two negative eigenvalues. The Hessian will be negative definite, and in this case P2 will be a maximum. So let us have a look at question 4. We're looking for the first iterate when we optimize this function using the Newton descent methods, right? So here is the first iterate. It's obtained from, well, the initial point, and it's obtained by taking one step. This is the one over here in the, well, Newton descent direction. The Newton descent direction is given over here, and, well, you need the Hessian and the gradient evaluated, in this case here in the initial point. If you plug in the values x is equal to 3 and y is equal to 3 in here, with c is equal to 2, this is the gradient that you obtain, and this is the Hessian that you obtain. The, well, Newton descent direction is minus the Hessian inverse times the gradient evaluated at the point where you are. So here it's at the initial point. We need the inverse of the Hessian. The Hessian is over here. So it's 1 over the determinant. This is what you've got over here. So we interchange those two and we change the sign of those two over here. If you multiply, well, this is what you obtain. So now we can plug in the expression of, well, this vector over here in here, and this is what we obtain. So this is the initial point. Here we take one step in the Newton direction. So here this is the inverse of the Hessian. This is this one. The minus sign comes from here, and this is the gradient evaluated at the initial point. If you do the calculations, you'll have to subtract 9 over 12, which is 3 over 4. And if you do this calculation over here, you have 9 over 4 for x1 and 9 over 4 for y1. We can check our result of question 1 very quickly in MATLAB. For that we have to do a surface plot of the function here. I've taken in this case c is equal to 2, which is the c that we have used in question 4. So here we have, well, the first candidate P1 and here the second candidate P2. So here for this one we should have a saddle point, and since c is positive for the second candidate P2, we should have indeed a minimum, and this is indeed what we obtain if we run the code, right? So this is the figure that corresponds to this part of the code. So here we have P1, and you can clearly see that you have a saddle point, right? Here we're looking in the vicinity of P2, which is the point 2, 2, and you can clearly see that it is a minimum. So it looks like the result is indeed correct. So what you can do is use the software that is given in the theoretical course to check our result of question 4. So we do one iteration, we use Newton descent method, we do a step size of 1. Here is the function. This corresponds indeed to c is equal to 2. We start from this initial point and then we start from here and we end up in x is equal to 225 and y is equal to 225, as you can see, and this is indeed the point that we have found, because 225 is indeed 9 over 4. Well, let us have a look now at question 5, which is a two-phase simplex method exercise. It's a quite standard exercise for this type of exam of optimization. You have to solve the problem that is shown on the screen. Try to do this by yourself as usual and push the pause button. Well, the first thing that we have to do is to transform our original problem and put it into a so-called standard format, right? And in the standard format we use a minimization instead of a maximization. That's quite easy. What you have to do is take the cost function and multiply it by -1. This is what we have done over here. In a standard problem we want equality constraints. Here we have inequalities, right? So in this case here we have smaller or equal, and we use a so-called slack variable. Here we have an inequality larger or equal than, and then we have to use so-called surplus variables. So we introduce 3 additional variables that have to be positive, of course, as are the original variables x1, x2, and x3. Well, there is no easy way to find a basic feasible solution for this standard problem. So what we'll do is, well, use this stage 1 artificial problem and add, well, 2 artificial variables, and we'll solve this artificial problem. Because for this artificial problem it's quite easy. to find a basic feasible solution. It's x4 is equal to 50, x7 is equal to 36, and x8 is equal to 10. When we will have solved this problem, and the solution should yield x7 and x8 are equal to 0, we'll have a basic feasible solution for our standard problem, and we'll be able to start stage 2. So we can start stage 1. Here we have the tableau that corresponds to the artificial problem, right? You can clearly see that it is indeed the artificial problem because the cost function is indeed x7 plus x8. So we're not quite ready to start with this tableau because, as we have said before, the basic variables are x4, x7 and x8, and in order to start making decisions we have to make sure that there are zeros above and below the pivots. This is clearly the case for the variable x4, but this is not the case for the variables x7 and x8. So what we'll have to do is to perform some row eliminations, right, to make sure that these elements here become zeros, so that we have, well, zeros above and below the pivots. So we have now performed these two elementary row operations, and here underneath we have found the following line which replaces the previous one. This is why I've crossed it out. And in this line what we obtain are the reduced costs. So we have seen in the course that to know which variable is going to become basic and join the basis, we have to take the reduced cost that is the most negative, right? If there is one that is negative, and here clearly, well, it's this -3, which indicates that x1 is going to join the base. Now we need to kind of see which variable is going to leave the base, right? And for that we compute this column over here. In this column what you do is take an element of this B column and divide by the corresponding element in the x1 column over here. So 50 over 2, 36 over 2 and 10 over 1. This is what you see over here, and here you need to select the element that is positive and smallest. So clearly it's this element over here. So we see that this is going to become the next pivot. x1 is joining the base, right? And of course x8 has to leave the base, right? This is the new pivot. We have to create zeros above and below the pivot, and this is why we need these three elementary row operations to create zeros over here, here and here. These row operations, well, it's kind of easy. We work with minus signs over here, so you have to pay attention. What you do is take the element that you need to eliminate, divide by the pivot to obtain the multiplier. Well, we obtain a new tableau in which x1, x4 and x7 are the basic variables. We obtain also new reduced costs, right? And we can use them to isolate, well, which variable is going to, well, join the basis the next time, and the reduced cost that is the most negative, if there is any, and here there is x6. So x6 is going to enter the base, and of course we need now to look at the variable that is going to leave the base. For that, what we do is compute this column. This is elements of this column divided by the corresponding elements in the column x6. So 30 over 2, 16 over 2, 10 over -1, so we have 15, 8 and -10. Here we have to select the element that is positive and smallest, so here clearly this is this one. So this is the next pivot, right? And we can now see that, well, this can no longer be a pivot, so x7 will leave the base. So this is our new pivot, right? And what we have to do now is create zeros above and below the pivot, and this can be done by using these elementary row operations. What we have to do also is to make sure that this pivot becomes a 1. So what we'll have to do is multiply this row by a half. Well, we can now perform these elementary row operations and multiply this row by a half, and then we obtain the following tableau, in which we see that all reduced costs are, well, 0 or positive. Okay, and we see here that we are at the end of stage 1 because we have the original cost with the cost that is associated of 0, and we see that since x7 and x8 have left the basis, we have a solution here with x7 and x8 is equal to 0. So in this artificial problem, we have indeed a solution with the artificial variables equal to 0. And what about the other variables? Well, the basic variables x1, x4, x6 are non-zero. You can clearly read their variables over here, and because we have a pivot over here, we have a pivot over here, and a pivot over here, right? So x1 is 18, x4 is 14, x6 is 8, and the other variables are 0. So here we have clearly a basic feasible solution that we can use for stage 2. And in stage 2, what we'll do is cross out these columns over here and replace this cost over here by the cost of our standard problem. We are now ready to perform stage 2, and this is the initial tableau of stage 2. Remember that we've taken, well, this tableau here, and we've crossed out columns x7 and x8, and we have of course used the cost associated to the standard problem. This explains here the -1, -1 and -2 coming from here. Remember that the basic variables are x1, x4, x6, right? Here are the pivots, and to start decision making, what we have to make sure is that above and below the pivots we have zeros. This is clearly the case for the variable x4 and x6, but this is not the case for variable x1. So what we should do is make an elementary row operation to create a 0 over here. Then you can do this using this elementary row operation. Well, when we perform this elementary row operation, this row that I've crossed out here in red becomes this row over here. We are now in a position to decide which variable is going to join the basis, and since this is the reduced cost that is most negative, well, we can see that x3 is going to join the basis. Now we have to see which variable is going to leave the basis, and this is why we compute this column over here. And this is really, well, the elements of the column B divided by the elements, the corresponding elements of column 3. So we have 14 over 1, 14, 8 over -1, -8, and 18 over 0, so infinity. So we have to take the smallest element that is positive, so this is clearly this element over here. So we see this will be the new pivot, and we can see now that x4 is going to leave the basis. This is our new pivot. We have to create zeros below this new pivot, so we have to create a 0 over here. This is done by this elementary row operation, and we have to create a 0 over here, and this is done by this elementary row operation. Once you have performed these two elementary row operations, you obtain the following tableau in which x1, x3, x6 are basic variables with the corresponding pivots shown over here. And in the last row, we have the reduced costs. We see that there is one that is negative. So this means that you can reduce the cost by letting x2 enter the base, right? So what we have to do now is decide which variable is going to leave the base, and for that we compute this column here in which we take the divide and the elements of the column B by the corresponding elements of the column x2. So 14 over 0 infinity, 22 over a half 44, and 18 over a half 36. So this is clearly the smallest positive element, right? So we know now that the pivot will be this element over here, and that x1 will have to leave the base. So this will become our new pivot. So what we'll do is multiply the row by 2 to make sure that the pivot becomes 1 again, and then we'll also perform elementary row operations to create zeros over here and a 0 over here, and this is done over here. If you want to know why you need this selection, right, of the smallest positive element, remember that this has to do with step 2 of the simplex method, and if you want more details, of course, you should have a look at the theory course. Well, when we perform these elementary row operations and this multiplication of the third row, we end up with the last tableau, and we can see that it's the last tableau because the reduced costs are all positive, right? So we can now read the final solution, right? We know that the basic variables are x2, x3, x6, but x2 and x3 are original variables from the problem, and as you can see, x2 is 36, x3 is 14, and x1, another variable from the original problem, is non-basic, so it is 0, right? And if we look at the slack variable and the two surplus variables, they are all 0 except the surplus variable x6 that you can read from the tableau is 4, right? So we can do some elementary checks. We can look at the cost over here. If we add x2 and 2 times x3, we obtain indeed 64, which is correct. Remember that minus 64, and the opposite of what you see over here, is the cost of the problem here, the standard problem, and 64 is therefore the solution of the original problem that was a maximization problem, right? So we can see over here that the first two inequalities are met with equality, whereas the last inequality is met with a surplus of 4, because indeed over here you have 0, there 14, and indeed you have this surplus of 4. And if you check, you will see that the two other inequalities over here are met with equality. Of course, we will check our results with MATLAB. We'll use the function linprog. You have to write the problem as a minimization problem, okay? But we can use inequality constraints. We have to pay attention because we have inequality constraints smaller or equal, and the two last equations in our problem are greater or equal constraints, so we'll have to multiply the two last equations by -1, and in our case we only have a lower bound on x, there is no upper bound. We will not use the equality constraints. Here is the very simple code that we can use to check this. So this is the cost function transform into a minimization. Here ax smaller equal to b. Notice that we have multiplied the two last equations by -1. There is only a lower bound on x, and then you can simply run the command linproc. If we do so, this is what you obtain. And as you can see, x1 is equal to 0, x2 is equal to 36, and x3 is equal to 14, which is exactly what we have obtained. And finally, let us have a look at question 6 over here, which is an optimization problem that you have to solve using the Lagrange multiplier method. So the question is to find the points of the circle in our cube that is defined by these equations that are furthest and nearest from the point 1, 1, 0. So you have to rewrite this as an optimization problem first, of course. But you can clearly see that this is indeed a circle, because this is the equation of a sphere in our cube. This is clearly the equation of a plane in our cube. So the intersection of both is a circle. Okay, so we have to find the points of this circle that are furthest and nearest from this point over here. So as usual, try to do this by yourself and push the pause button. Well, first of all, let us look at the distance of a point xyz to the point 1, 1, 0, and you know for a very long time that this is really the square root of, well, x minus 1 squared, y minus 1 squared, z minus 0 squared, right? But this square root is kind of annoying, so what we'll do here is, in our optimization problem, work with the distance squared, as we have done very often in the course, right? So our optimization problem, we can write it like this: minimize or maximize, because we speak of furthest and nearest. Well, the distance squared, this is the distance from xyz to the point 1, 1, 0, subject to the fact that, of course, xyz lies on the circle, right? And this you can rewrite as follows by saying that, well, xyz on the circle is an xyz that meets these two equations, right? So this is here our optimization problem that we can now solve, and it's appropriate to solve it using the Lagrange multiplier method, because, well, the function, the cost function over here is nonlinear. You have two constraints, and one of the constraints is nonlinear as well. If you were blocked by writing this optimization problem, you can now continue by yourself and push the pause button and solve this optimization problem. Well, the first thing that we have to do is to write the Lagrange function, which is in terms of the original values x, y, z, and two Lagrange multipliers, because there are two constraints. Okay, here we recognize the original cost function, and here we add two terms. Well, the first term is the first Lagrange multiplier times the constraint. Don't forget the 1 over here and pass it on the other side. And, well, the last term is the second Lagrange multiplier times the second constraint. We have transformed our optimization problem that is constrained into an unconstrained optimization problem of the Lagrange function with two additional variables. That's the idea, right? So what we can do is find the critical points of this Lagrange function simply by taking partial derivatives with respect to the 5 variables, the original variables plus the 2 Lagrange variables, and set those, well, partial derivatives to 0. And this is what you obtain. You will see that the calculations are quite easy. As usual, in the last two equations, you recover the constraints that you see over here, right? Now it's just a matter of solving this system of equations. Quite easy in this case. you isolate x, y, and z as a function of lambda and mu. And this is what you see over here, right? And then you inject them in the two constraints. We'll start with the last constraint. If you do this, and if you add x, y, and z, this is what you obtain, right? And this has to be equal to 0. This means that mu is equal to 4/3. And now you can inject this over here and obtain a simpler expression for x, y, and z, right? Now we inject this thing here in the fourth equation, so the first constraint, and you obtain an equation in terms of lambda. If you solve this equation and you see that it's not very difficult, you see that lambda is equal to -1 plus minus the square root of 6 divided by 3. If you inject this in here, you will see that there are some simplifications, the 2 over here and the 3's over here. You obtain this expression here with a plus and a minus, and you can clearly see that, well, the plus is corresponding to a minimum because you have something positive minus something, so you end up with something smaller in the square terms over here. So if you simplify, you will see that, as I said, the elements coming from the plus will generate a minimum, whereas in this expression of lambda, the minus will yield the maximum. And this concludes question 6, and this concludes also the solution of the optimization exam of June 2023.